The universe doesn't just have a future, it has an ending, and has a surprising number of ways to get there in a variety of cosmological models, and we don't know which one it is. It may fade into heat death, tear itself apart in a big rip, unravel more slowly in a little rip, collapse backward in a big crunch, or turn that collapse into a big bounce. It might collapse chaotically in a big smoosh, snap at a sudden singularity in a big break, get rewritten in vacuum decay in a big slurp, or become a battleground of competing vacuum bubbles. It might decay through proton decay, fade through dark matter decay, settle into an iron star era, leave behind Planck stars, or restart through conformal cyclic cosmology. It might lose the meaning of distance through spacetime dissolution, rewrite the rules through dimensional shedding, collide with another brain in the big snap, or run into the informational limits of a holographic boundary freeze. And the universe lasts long enough, it might become dominated by Boltzmann Brains, repeat through Poincaré Recurrence, collapse into thought through an omega point, or end as an information graveyard, where every remaining particle is alone with itself. Today we're going to walk through all of them, from the well-supported to the very iffy. What they are, what they look like, and which one the universe actually seems to be headed toward. There's a lot of them, so you might want to grab a drink and a snack, and hit those like, subscribe, and notification buttons while you're at it. Heat death, the default ending. If you had to pick one ending for the universe, the one that requires the fewest assumptions, the least new physics, the smallest leap beyond what we already observe, it would be heat death. Not because it's dramatic, not because it's exciting, and not because it's actually hot, but because it's what happens if nothing goes wrong. Right now, the universe is expanding, not just expanding, but accelerating outward, driven by what we call dark energy. Galaxies are drifting apart. Over time, that drift becomes isolation. Assuming that expansion continues, it's a fiercely debated topic, then give it long enough and every galaxy beyond our local group slips over the cosmic horizon, forever out of reach. The night sky empties, not because stars have died yet, but because everything else has simply moved too far away to see. This is a long time off, but over the next several billion years, our galaxy will merge with all the other locals, into what we call the Milk-Andromeda Galaxy. Instantly, I hate that name. Our sun will still be around when that begins, and in its red giant and white dwarf phases as that wraps up. Over the next 100 billion or so years, as that white dwarf cools, that big merged galaxy will grow increasingly isolated as all the other merged galaxies flee over the cosmological horizon from Hubble expansion. This is not a dark era. This point star formation has dropped off a little, but not much, and there's actually way more stars, as all the red dwarfs, dim though they are still around, and tons of new stars are born all the time. Eventually, though, things turn down. Star formation slows as gas clouds are used up or dispersed. The bright, short-lived stars go first, followed by long-lived red dwarfs that can burn for trillions of years. For a while, the universe actually becomes quieter and redder, dominated by these dim, efficient stars that sip their fuel slowly. But even they do not last forever. By around 10 to the 14th or 15th years, the last conventional stars burn out. What remains are stellar corpses, white dwarfs, neutron stars, black holes, and the occasional faint glow of brown dwarfs and stellar remnants interacting. This is the degenerate era, a universe lit not by fusion but by leftovers. Over even longer spans of time, those remnants begin to fade too. White dwarfs cool into black dwarfs, neutron stars settle into cold, dense spheres, and the only major engines left are black holes, slowly feeding on whatever remains. Nothing remains in stable orbits. Everything either gets matured into an ejection or a merger, and even the most stable orbits will drain down via gravitational radiation over our quadrillion to a septillion years. You have drifting objects ranging from black dwarfs and ejected planets down to lonely atoms, but black holes dominate this now dark universe, and then eventually even they begin to disappear. Thanks to Hawking radiation, black holes are not eternal. They very slowly leak energy, shrinking over unimaginable spans of time. A stellar mass black hole might take 10 to 67 years to evaporate. The supermassive ones at galactic centers last even longer, up to 10 to the 100th years or more. But they do go. And when they do, they release their final burst of radiation into a universe that is already almost perfectly uniform. We've talked about living around them in our first Civilizations of the End of Time episode, Black Hole Farming, and the struggles to continue in this and various other cosmologies is documented in our Civilizations of the End of Time anthology, How Intelligence Survives the Death of the Universe. The shortest lived of these, the ones formed from the least massive star that could die to make one, live for 10 to the 68th years. The longest, massing more than a galaxy, would live about 10 to the 100 years, or 1 Google years. If you're curious, that number for 10 to the 100th was coined almost 100 years ago by the 9-year-old nephew of mathematician Edward Kasner. Spelled Googol, but it was the inspiration for the name of the giant computer company. Page and Brin wanted something to name their search that implied organizing vast amounts of information. They misspelled it when registering the domain name, though, Google, but amusingly, a popular theory for how the young kid came up with the name was from a comic strip character, Barney Google, which is still in print, and the character's name is spelled like the Google we all know and love, who owns YouTube. All praise the algorithm, and don't forget to like and subscribe to the show to appease that algorithm. For creatures to whom a century-long comic strip still running is impressive, it is almost meaningless to contemplate civilizations lasting as long as black holes, and it might not be viable. But if it is, with a few possible exceptions, this is when you run out of energy available to run civilizations. At that point, you're left with a thin, diffuse soup of low-energy particles and radiation, spread across a volume so vast that density becomes almost meaningless. Each little atom or dead planet remnant is drifting along in a universe of its own, trillions of light years from neighbors, whose they hadn't been, they'd have been swallowed by some bigger remnant billions of eons before that. A remnant that either blew up as a supernova or expiring black hole long ago. No stars, no galaxies, no structure. Just a universe that has reached maximum entropy, where everything that can happen has happened and nothing meaningful is left to occur. This is heat death. Not an explosion, not a collapse, just a universe run out of differences. It is not a hot place in the sense of high temperature. Indeed, it's reached temperatures so low they only mean anything in negative exponential notation. But that's merely because it's spread out so wide. Virtually all the energy in the universe at this point is heat. Some is still radiation in the form of drifting photons, all redshifted to wavelengths wider than galaxies. Some are neutrinos, and some energy is still in mass energy, those rare atoms and even perfectly spherical planets and remnants meandering in the utter void. Nothing is rotating anymore. Even in a near-perfect vacuum, objects will slow their rotation from interaction with virtual particles. So the dominant energy in this cold universe is heat energy, the leftover useless entropic type of energy. I should note, however, that there is an alternative possibility for these black holes dying. Some approaches to quantum gravity suggest that black holes might not evaporate completely. Instead, as they shrink, they could reach a minimum size set by quantum effects and stabilize as tiny, ultra-dense remnants, sometimes called Planck stars. Even inside this theory, there is disagreement depending on other cosmologies and theories, but the minimum possible mass would be 1 Planck mass, which is vastly smaller in size than atomic nuclei and about as massive as a speck of dust. Some other values can go as high as milligrams or even an entire gram. Not too impressive an end for those monsters that used to mass as much as many stars or even whole galaxies. In that case, the universe doesn't end as a thin gas of radiation. It ends instead as a graveyard of microscopic, nearly indestructible objects. Cold, silent, and incredibly dense, scattered across an otherwise empty cosmos. Proton decay. Does matter even survive? But even within heat death, there is an important question that changes how this ending actually plays out. Does matter itself last that long? Protons, the building blocks of atomic nuclei, are assumed to be stable in the standard model of particle physics, but many theories that try to go beyond it, particularly grand unified theories, suggest that protons might not be truly eternal. Instead, they could have an incredibly long half-life, something on the order of at least 10 to the 34th years, or perhaps vastly longer. Personally, I never liked the theory or supersymmetry, which it descends from and which was a lot more popular back when I was a physics student in the late second millennium. The science doesn't care about my preferences or opinions, but I'll admit that I'm glad the theory has fallen out of favor, as we haven't observed proton decay yet. That deserves a caveat, though. Experiments have placed lower limits on how long protons must last, but longer than we've checked so far is very much not the same as forever. And as long as that half-life sounds, 10 to 34 years is still a billion, trillion, trillion times shorter than the shortest-lived black hole. That matters because if proton decay does occur, then matter as we know it slowly dissolves. Atoms fall apart. Nuclei break down into lighter particles. Eventually what remains a universe dominated by radiation and elementary particles, long before black holes have even finished evaporating. In that version of heat death, structure simply disintegrates. But if protons do not decay, if they are truly stable, then matter persists, and that opens the door to a much stranger, much slower future. Because even in a cold, dark universe, quantum mechanics never fully turns off. Given enough time, absurd amounts of time, particles can tunnel, rearrange, and settle into more stable configurations. And that leads us to one of the most bizarre possibilities for the far future, a universe where everything, slowly and silently, turns to iron. But before we get there, we take a step back, because heat death is only one possible ending, and some of the alternatives are far less gentle. The violent alternatives. Heat death is what happens the universe keeps doing what it's doing now, but that if matters, because small changes in how expansion behaves, particularly how dark energy evolves, can lead to endings that are not slow or quiet at all, but sudden, destructive, and in some cases surprisingly near in cosmic terms. The Big Rip, when expansion wins too hard. Right now, dark energy appears to act like a constant, a steady push outward that accelerates expansion but doesn't grow stronger over time. But we cannot take for granted that it will remain the same. After all, we don't know what it is or where it comes from, if anywhere. There could be some reservoir of another reality it is draining out of and it could empty, or tear a wider hole or get clogged, so to speak. If it isn't constant eternally, if dark energy increases as the universe expands, you need a very different future. In this scenario, often called the Big Rip, expansion doesn't just continue, it accelerates faster and faster, until it begins to overwhelm every other force in the universe. At first, nothing seems unusual. Galaxies drift apart a bit faster. The large-scale structure thins out more quickly. But eventually, the expansion becomes strong enough to overcome gravity on smaller and smaller scales. Galaxy clusters unbind. The individual galaxies begin to come apart. Their stars no longer held in orbit. Then solar systems dissolve as planets drift away from their stars. Nor does it stop there. As the expansion continues to intensify, it begins to overcome electromagnetic forces. Molecules are pulled apart. Atoms themselves are stretched until even nuclear forces can no longer hold them together. In the final moments, space-time expands so violently that every bound structure, down to subatomic particles, is torn apart. And unlike heat death, which takes effectively forever, the Big Rip happens in a finite amount of time. We don't know what that time would be, in spite of the overhyped news articles saying 20 billion years. There's a constant involved. If you set to a certain value, you get a certain time. But whether it was 20 billion or 20 trillion or 20 Googles, after the black holes are dead, there is a final moment. A last instant where distances diverge, and the universe becomes infinitely large, infinitely dilute, and completely unbound. It's not a quiet ending. It's the universe being pulled to pieces. The Little Rip, the endless unraveling. As I said, we don't know how long it would take for the Big Rip to happen, and the popular figure is simply the byproduct of running the calculation on an arbitrary and startling number. This is the Little Rip. Here, dark energy still grows strong over time, but never fast enough to produce a true singularity. There's no final moment where everything breaks at once. Instead, the process just keeps going. Galaxies eventually drift apart. Then stars lose their grip on their planets. Then stellar systems themselves slowly dissolve. Given enough time, even atoms and nuclei can be unbound, not in a sudden snap in a long, drawn-out erosion of structure. There's no deadline you can point to, no end of the universe date circled on the calendar, just an endless progression of losses, each one a little smaller, a little more local, but just as final. For a civilization, this is arguably worse than the Big Rip. In a Big Rip, there's a clear timeline. You can calculate how long you have. In a Little Rip, there's no such luxury. You might outrun the dissolution of your galaxy. You might migrate to more stable regions. But eventually, the forces holding you together, your structures, your materials, your atoms, begin to fail as well. And there's nowhere left to run. The Big Crunch. When gravity strikes back. Of course, there's another possibility entirely. What if expansion doesn't win? What if instead gravity eventually takes over again? In the early days of modern cosmology, this was one of the leading ideas, that the universe might expand for a while, slow down, and then reverse, collapsing back in on itself in a big crunch. This is a reasonable enough assumption, as before this it was assumed the only reason the universe hadn't done so, in steady-state models or earlier variations, was because the universe was infinite in size, so it had no center to fall into. Everything was tugged more or less equally in every direction at once. The Big Crunch takes this concept up in the finite universe of the Big Bang. In that scenario, the distant future looks very different. Galaxies that were once receding begin to slow, then drift back together. The night sky, instead of emptying, grows brighter over time as distant structures come back into view. Background radiation, stretched thin by expansion, begins to compress and heat up again. Temperatures rise, densities increase. Stars that had long since died might be replaced by new intense bursts of energy as matter is forced together again. And eventually everything collapses toward a final, hot, dense state, perhaps similar to conditions at the beginning of the universe itself. Omega Point cosmology, which we will return to in a bit, contemplates civilizations using this collapse to run themselves and perhaps stretching out to an infinite timeline. But cosmologically, it's a straightforward option, a cosmic reversal. But even this neat picture turns out to be a bit too tiny. The Big Smoosh, a chaotic collapse. If the universe does collapse, there's no guarantee it does so evenly. After all, it didn't spread out that way. As we discussed in our episode on cosmic strings, that unevenness probably dates back to much less than a nanosecond after the Big Bang, during the theorized period, correctly but confusingly named the inflation epoch. In more detailed models, particularly those involving anisotropic dynamics, the collapse can become chaotic. Different directions shrink at different rates. Space stretches along one axis while compressing along another, then flips, oscillating faster and more violently as the end approaches. Instead of a smooth implosion, the universe becomes a kind of cosmic taffy prolor, stretching, squeezing, and distorting everything inside it. These oscillations would generate intense gravitational waves, extreme tidal forces, and rapidly changing conditions that would tear apart structures long before the final collapse is reached. So, even in a universe where gravity wins, the ending may not be a clean return to the beginning. It may be chaotic, violently unraveling on the way down. This matters for anyone hoping to surf the wave of a dying universe into a hopeful future one. And speaking of that, the Big Bounce, the reset button. The Big Crunch or Smoosh both raise an obvious question. If the universe collapses, does it stay collapsed, or does it bounce? In various models, ranging from older oscillating universe ideas to newer quantum gravity approaches, the Big Crunch is not the end, it's just a transition point. The universe contracts into a high-density state, but instead of forming a singularity, new physics kicks in. Quantum effects, extra dimensions, or unknown forces halt the collapse and reverse it. A new expansion begins. A new Big Bang. In some versions, this happens over and over again, an endless cycle of expansion and contraction. In others, the bounce wipes the slate clean, resetting conditions each time. But there's a problem lurking in the background. Entropy. Each cycle should increase disorder, making it difficult to explain how you get a fresh, low entropy beginning every time. Entropy, the laws of thermodynamics and conservation of energy, All very stubborn problems when we start talking about the beginning and end of time, and even more so when the Big Bang becomes a recurring chapter opener instead of a one-time event. Modern bounce models try to work around this, often invoking new physics or hidden degrees of freedom. But like many alternatives to heat death, they require assumptions we don't have evidence for. And it's worth pausing here for a side note, though this episode probably has too many of those already. There's a tendency to imply that physicists have some sort of answer for how something can come from nothing, ex nihilo. We absolutely do not. We know a lot more about reality these days, and how our chunk of it appeared and evolved. We have no new answers for the ex nihilo problem that's plagued philosophers and theologians for millennia now. What we have are some mathematical ideas for how something might arise from very simple starting conditions, the sort that kinda sorta might work, and a lot of quantum behavior where things seem to pop out of nowhere. But that mostly leads us to suspect that nowhere isn't really nowhere at all. This is what we'll refer to later as a false vacuum. It turns out that nothing is often packed with quite a lot of something. It's a bit like accounting. If I have a huge amount of some particle and equal amounts of some of its opposite, and they all collide and cancel out, I might end up with a net total of 0. That does not mean nothing happened. It's no more nothing than a company that makes billions of dollars and spends billions of dollars, somehow not existing just because it reported 0 net income. If that were the case, there would be a lot of very non-existent companies out there. And that's really the issue here. When physicists talk about nothing, we are almost always assuming something is already there. A 0 in an equation means it is balanced, not an absence of existence. Quantum fields already exist. The laws of physics already exist. Vacuum energy already exists. Sometimes even space-time is already in the picture. That's an awful lot of something in that nothing. Real nothing doesn't have anything in it, maybe not even rules or math, as we'll need to consider in a bit. So at this point we've covered the major contenders: the slow fade, the violent tear, the collapse, and the reset. But these are still in a sense normal endings. They assume the laws of physics keep working. Indeed, they were working maybe before the universe existed. That space, time, and matter continue to behave in recognizable ways. And that assumption might not hold, because some of the strangest possibilities for the end of the universe are not about how things end, but about what happens when the rules themselves stop applying. When the rules break. Up to this point, every ending we've talked about assumes something important. The laws of physics keep working. Maybe they lead to a cold universe, maybe a violent one, maybe even a reset. But in all of these, the rules still hold. Cause leads to effect. Space and time still means something. But there are scenarios where that assumption fails. Not because the universe runs out of energy, not because gravity wins or loses, because the rules themselves stop behaving in ways that make sense. The Big Break, when the timeline snaps. One of the strangest of these is sometimes called the Big Break, a type of sudden singularity. In this model, the universe expands normally right up to a specific moment in time. Galaxies drift apart, distances increase, and everything looks fairly ordinary. But something is going wrong underneath. In cosmology, pressure isn't just about things pushing outward. It actually affects how space itself expands. Dark energy has a kind of negative pressure, which is what drives the acceleration of the universe in the first place. Normal, positive pressure tends to help gravity pull things together. It's a bit like being deep underwater, where pressure comes from all directions and compresses everything. The dark energy does the opposite. It is more like tension than pressure, as if space itself is being stretched apart everywhere at once, causing everything to move apart. In this scenario, the effect doesn't stay steady. The pressure starts heading toward negative infinity, not gradually but sharply, while the expansion rate itself stays finite. So space keeps expanding at a reasonable pace, but the push behind the expansion becomes mathematically extreme. And then, at a precise moment, the equations just stop giving meaningful answers. There is no runaway expansion like the Big Rip, no collapse like the Big Crunch. Just a last valid moment, and nothing you can meaningfully describe after it. The universe doesn't end because it runs out of energy, it ends because the math describing it stops working. It's less like a fire going out and more like a film reel snapping in the projector. Vacuum decay, the big rewrite. If the Big Break is math failing, vacuum decay is something else entirely. Here, the universe doesn't wind down, it gets replaced. The laws of physics depend on the state of the vacuum, the lowest energy configuration of all fields. But it is possible that what we call the vacuum isn't the lowest state at all. It might be a false vacuum, stable for now but not permanent. If that's the case, then somewhere, at some random time, a tiny region could tunnel into a lower energy state. A bubble of true vacuum would form, and once it does, it expands outward at nearly the speed of light. Inside that bubble, the rules change. Fundamental constants could shift, forces could behave differently, and matter itself might not even be stable anymore. And the bubble does not stop. It expands, rewriting everything it reaches. There is no warning, no signal ahead of time. If it happens, it reaches you at the same moment it destroys you. Not an explosion, nor a collapse. Instead, just one set of physical laws replacing another. We've got a full episode on vacuum decay if you want to dive deeper into that one. And there's an even stranger possibility. If multiple regions decay into different vacuum states, you don't get just one bubble, you get many, expanding, colliding, and competing. The Indian universe might become a kind of phase transition, where different versions of physics spread and clash, and the most stable one wins. Not just a rewrite of reality, but a competition between realities. As we're seeing, the idea of an ending starts to get fuzzy. These aren't just the ways the universe runs down, they're the ways the rules themselves can change or be replaced. But even these aren't the strangest possibilities, because some endings don't break the rules at all. They follow them all the way down, into a universe where matter slowly changes into something else, and everything becomes quieter than we usually imagine possible. To see that, we need to return to heat death and follow it much further. The deep time heat death. When we talk about heat death, we usually stop at the point where the stars are gone, black holes have evaporated, and the universe is cold and diffuse. That already feels like an ending. But it isn't the end of the story. It's the point where the universe becomes quiet enough that the main changes are slow, subtle, and easy to overlook. Because even in a universe that cold, nothing is ever truly frozen. Quantum mechanics does not switch off, time does not stop passing, and given enough time, even the smallest possibilities eventually happen. Dark matter decay, when gravity fades away. One of the assumptions built into most heat death scenarios is that dark matter is stable. It acts as the gravitational scaffolding of the universe, helping hold galaxies together and shaping large-scale structure. We don't actually know that it lasts forever. If dark matter particles are unstable, even on extremely long timescales, they could slowly decay into lighter particles or radiation. As that happens, something subtle but profound occurs. The gravitational glue of galaxies begins to weaken. Stars that were once held in orbit drift away, along with much of the hotter gas in the galaxy. Galactic structures loosen and dissolve from the inside. This is different from expansion pulling things apart. In that case, structures are stretched externally. Here they simply stop holding together. Even before the last remnants of stars fade, the frameworks that once kept matter assembled begin to disappear. You don't just get an empty universe, rather you get one that forgets how to stay assembled. Now, there is a constraint on how fast this could happen. If dark matter were to decay into particles that interact with normal matter, or produce detectable radiation, we would expect to see this effect already, in gamma rays, cosmic rays, or distortions in the cosmic background. Since we do not, we can place a lower bound on its lifetime. Right now, that lower bound is on order of a quintillion years or more. That's roughly the same timescale over which the last natural stars are expected to fade out. So even if dark matter does decay, it likely doesn't play a major role in shutting down star formation or unbinding galaxies early on. But over a longer stretch of time, it could quietly erase what structure remains, leaving behind a universe that is not just dark, but dynamically hollow. The Iron Star Era, a universe that settles. Now return to that earlier fork in the road. What if protons do not decay? What if matter lasts? In that case, the far future becomes something much stranger. Because over absurd stretches of time, quantum tunneling allows matter to rearrange itself into more stable configurations. Not quickly, not even slowly by any normal standard, but inevitably. A good way to picture this is mechanical settling. Take a pile of material and give enough nudges and vibrations, it will gradually compact, flatten, and settle into a denser arrangement. We see this even at the planetary scale, where worlds slowly relax into near-perfect spheres over time. The same idea applies at the nuclear level. Every arrangement of protons and neutrons has a certain binding energy, and systems tend to drift toward lower energy configurations when they can. When stars fuse hydrogen to helium, 4 protons rearrange into a tight structure of protons and neutrons. The total mass energy is lower, and the difference is released as energy. That's what powers stars. But this process does not continue forever. At higher masses, nuclei become less stable. Elements like uranium and thorium can be formed in extreme events, but they slowly fall apart over time. Even uranium-238, one of the most stable heavy nuclei, only lasts billions of years. At the heavy end, the last stable nucleus is lead-208, while bismuth-209, once thought stable, turns out to decay on timelines about 10 quintillion years. At the lighter end, fusion effectively stops near iron. When massive stars begin fusing silicon into iron, they hit a dead end. Iron cannot release energy by fusing further, and that triggers the collapse that leads to supernova explosions and the formation of neutron stars or black holes. Of iron isotopes, iron-56 sits at the bottom of this energy curve, with nickel-62 edging out slightly as the most tightly bound nucleus. Nickel-58 and nearby isotopes come close as well. Over enough time, quantum tunneling allows nuclei to slowly shift toward these lowest energy states. Protons and neutrons can rearrange, occasionally flipping configurations in ways that slightly lower total energy. Given enough time, those rare events add up. Matter drifts toward the iron peak. We call the result iron stars, so that's a bit of a simplification. In reality, they will be made of iron group nuclei, mostly iron and nickel, with smaller amounts of nearby elements. White dwarfs, neutron stars, and even planets would slowly transform into cold, dense spheres of this material. No light, no fusion, no activity, just vast numbers of inert, nearly perfect spheres, scattered across an ever-expanding universe. Not a universe that dies, but one that settles. But even that isn't the final state. Given enough time, on the order of 10 to the 1500 years or more, these objects can undergo further quantum transitions. Entire chunks of matter can collapse into black holes through tunneling processes. From there, the story continues as before. Black holes form, black holes evaporate, and the universe returns, once again, to radiation. If you could speed that process up, you'd see something almost dynamic. A planet slowly smoothing into a perfect sphere, settling into iron group matter, then eventually collapsing and releasing energy in a final outburst. That outburst might take quintillions of years, but at that scale, that's an instant. More importantly, it means there is still energy available, even this late in the life of the universe. Energy life might use to continue itself or begin over again. A point we explore more in our episode on iron stars and in the Civilizations at the End of Time anthology. A universe of almost nothing. By this point, what remains is difficult to even describe as a universe in the way we usually mean it. Particles are so far apart that interactions are rare. Energy is so evenly distributed that no useful work can be extracted. There are no gradients left. Nothing to power motion, change, or complexity. And yet, things still technically happen. A particle might interact with another after an absurdly long time, or maybe not quite as absurd if proton decay is real. Still, even then, electrons and positrons might still occasionally encounter each other to form positronium atoms, and strange new matter built out of that. A fluctuation might briefly create a localized pattern. But these are isolated, fleeting, and disconnected events. There's no structure tying them together. No systems, no processes, no history. Just a thin scattering of particles and radiation, drifting forever. And this is the key point about heat death. It isn't really about everything going away. Instead, it's about everything becoming the same. No hot and cold, no dense and empty, no organized and disordered. Just uniformity. Because time, in any meaningful sense, depends on change. And in a universe where nothing meaningfully changes anymore, it's hard to say that time still exists at all. And maybe it doesn't. But even this is not the strangest possibility, because all this assumes that space still exists, that matter still exists, and that the universe is still something you could, in principle, describe. And there are ideas that go one step further than that. Ones where it isn't just matter or structure that fades away, but space itself. Conformal cycles, when the end becomes the beginning. There is one idea that takes heat death and turns into something very different. Proposed by Roger Penrose, conformal secret cosmology suggests that cold, empty future of the universe may not really be the end at all. I'll note from the outset that we have an episode deep diving this theory too, so we will summarize today. In the far future, after black holes have evaporated and all massive particles have either decayed or become irrelevant, the universe is left with only massless particles. Photons, possibly gravitons, and a universe made only of massless things, something strange happens. Scale stops mattering, and time stops occurring. See, massless particles experience no time themselves. Things with mass experience time, and as a larger portion of energy comes from different things, like kinetic energy, as they approach the speed of light, the rate at which they experience time slows more and more. It becomes proportional to the percentage of themselves that is something besides mass. If all that is left is massless particles that experience no time themselves, then nothing is actually occurring. Moreover, if nothing has mass, then there is no meaningful way to define size or distance in an absolute sense. A universe that is infinitely large and one that is infinitesimally small become mathematically equivalent. And even if it was all packed into a fraction of a second, an awful lot went on in terms of spot phases and events in the Big Bang's near instant, including a period where things with mass began to appear, and before which they did not exist. And it opens the door to a surprising possibility. The infinitely stretched, cold, empty universe at the end of time can be reinterpreted as the hot, dense beginning of a new one. Not through a collapse, not through a bounce, but through a kind of rescaling. The end of one universe becomes the beginning of the next, simply because there is no longer any difference between the two. In this view, heat death is not the final chapter, it's just a transition between aeons. When reality itself starts to fail. Up to now, even in the deepest version of heat death, we've assumed something basic. That space still exists, that distance still means something, that the universe is still a place even if it's an empty one. But some of the more modern ideas in physics suggest even this might not be guaranteed, that space-time itself may not be fundamental. There could be something that emerges from deeper, more abstract structures. And if that's true, then the universe might not just be about matter fading away. It could be about reality itself losing the structure that makes it recognizable. Spacetime Dissolution, when distance stops meaning anything. One of the more intriguing ideas in modern physics is that spacetime may not be fundamental, but emergent. That what we perceive as distance in geometry might arise from patterns of quantum entanglement. Normally, we think of space as the stage where things exist, and entanglement is something happening inside it. But this idea flips that around. It's just the connections come first, and we call space is just how those connections are organized. This is often summarized in the conjecture ER equals EPR. EPR refers to quantum entanglement, where two particles share connection no matter how far apart they appear, our spooky action at a distance. ER refers to Einstein-Rosen bridges, or wormholes, connections in spacetime itself. The conjecture suggests that these are really the same thing viewed in two different ways. Not that entangled particles are sending signals through space, but that their connection can be thought of as a kind of space-time link. In very loose terms, that spooky action at a distance might be understood as two particles connected by an extremely tiny, non-traversable wormhole. If that picture is correct, then the smooth fabric of space is really a large-scale pattern built from these underlying quantum connections, the fabric of space-time itself. Distance isn't something fundamental, it's something that emerges from how strongly things are connected, and like any pattern, it can break down. In a universe heading toward maximum entropy, information becomes more and more randomized. Correlations fade and structure disappears. And as spacetime depends on those correlations, then eventually it may begin to lose coherence as well. Not in a dramatic way, not with explosions or collapses, but quietly, gradually, until the idea of distance itself no longer applies. At that point, it doesn't really make sense to say the two particles are far apart, or close together, or even located anywhere in particular. The universe doesn't expand, doesn't contract. It just stops being spatial. The map doesn't go blank. The paper itself disappears. Dimensional shedding, when the rules change. Another possibility comes from theories that suggest our universe has more dimensions than the three we experience. This is common in models like string theory, and once again we have an episode deep diving that topic, which includes brain collisions, which you may have heard of, where two brains smash together and either sets off big bangs or obliterates existing universes, and we'll get to that in a minute. However, it's not the only doomsday option from string theory. In many versions of string theory, there are additional spatial dimensions that are compactified, curled up so tightly that we don't notice them. The size and stability of those dimensions depends on delicate energy balances. If those balances shift, even slightly, the structure of the universe could change. An extra dimension might begin to expand, or one of our familiar dimensions could start to contract. Either way, the laws of physics would no longer behave the same way. Gravity, for instance, follows an inverse square law in 3 dimensions. If space suddenly had 4 large dimensions, that law would change. Orbits that were once stable would no longer be. Stars might collapse or disperse. Galaxies could lose their structure almost instantly. This wouldn't necessarily look like an explosion or a collapse. It would look like the rules quietly shifting underneath everything. And once they shift, nothing built under the old rules can survive for long. Not the end of the universe. The end of the version of physics that made it possible. The Big Snap, a collision beyond our dimensions. There are also models where our universe is not all there is, but kind of surface and bed into a higher dimensional space. In these brain cosmologies, our universe is a 3-dimensional slice floating in a larger structure. Other such slices could exist nearby, separated from us in dimensions we cannot directly access. In some versions of this idea, the distance between these brains changes over time. If they move apart, nothing much happens, but if they are pulled back together, the consequences are extreme. A collision between brains would release enormous energy, and have to reset conditions entirely. From the inside, it would look like the universe ending in a hot, dense state, something very much like a Big Bang. But the cause wouldn't be a collapse of space, it would be a collision through dimensions we don't normally perceive. Not everything falling inward, rather, everything colliding sideways. Pausing for a moment to assess, we're seeing at this stage of our episode that the idea of an ending has changed quite a bit. Often doesn't mean a return to nothing at all, which, as we've already discussed, is a very charged and debatable term itself. We're no longer just talking about matter running down or structures breaking apart. We're talking about the possibility that space, time, and the laws themselves are not permanent features of reality. That they can shift, dissolve, or be replaced. But there's one more layer to this. Because even if space and physics remain intact, there's still a deeper limit the universe may run into. Not a return to nothingness, assuming that was ever the case. Not a limit of energy, not a limit of structure, but a limit of information itself. When the universe runs out of information. So far, every ending we've looked at has been about something physical. Energy spreading out, matter breaking down, space expanding or collapsing. But there's another way to think about the universe, as information. Every particle, every field, every interaction carries information about the state of reality. And some theories suggest there may be a fundamental limit to how much information the universe can contain or process. If that's true, then the final stage of the universe might not be about energy or matter at all. It might be about hitting the limits. Holographic Boundary, when reality hits resolution limits. One of the more surprising ideas in modern physics is the amount of information a region of space may scale not with its volume, but with its surface area. That comes from what's known as the holographic principle. In simple terms, it suggests the 3-dimensional universe we experience could be described by information encoded on a 2-dimensional boundary. For a quick context, in a 3-dimensional case, you add information to a bucket, individual dots or pieces of matter. 3-dimensional information storage, every individual bit you would add to a volume is one more piece of information, and thus it scales 3-dimensionally just as volume does, because that's how many bits you can add into that system. In this case, it will be closer to how many dots you can put on a 2-dimensional screen. Now, take that idea to the far future. As the universe expands and entropy increases, information becomes more and more spread out. Eventually, you approach a maximum entropy state where all available information capacity is used. Once we arrive here, there's no room left for new distinctions, or no new patterns, new complexity. The universe can still exist, but can no longer change in meaningful ways. The bucket, or two-dimensional sheet of paper, is full. Another way to think about it is as resolution. If you ever zoomed in too far on an image, you reach a point where adding more zoom does not reveal new detail. You see bigger pixels. In this scenario, reality itself reaches that limit. The universe doesn't go dark, it just runs out of detail. At this juncture, I think it's worth pausing for a moment of caution. Many of these ideas arise or fall on mathematics, and the assumption that math or information is something physically real, not just a language we use to describe reality. That might be true. We often treat mathematics as a kind of universal language, something deeper than the universe itself. But as we discussed in Alien Mathematics, that assumption may be doing more work than we realize. So we talk about limits of information or reality running out of bits. It is worth remembering that we are leaning heavily on that framework. It may describe the universe perfectly, or it may just be the best tool we have for describing something deeper. As we move into the more information-based endings in this next section, it is worth keeping that question in mind. Boltzmann Brains, when randomness becomes everything. There's another strange consequence of a high-entropy universe. Even in a nearly uniform state, random fluctuations still occur. Given enough time, those fluctuations can produce temporary structures. Usually they are small and meaningless, but over vast stretches of time, even extremely unlikely events can happen, including the spontaneous formation of something complex, like a brain. A fully formed, self-aware structure, complete with false memories and perceptions, flickering briefly into existence before dissolving again. These are often called Boltzmann brains, and while we typically picture them as a human mind assembled in complete form as part of a thought experiment, you could have much bigger minds appear, and it is just as likely to be the minimum brain or computing apparatus needed to self-expand to something bigger. Indeed, it is vastly more likely the simpler ones would appear. Regardless, in our universe at least, even the simplest one is probably way less likely than normal evolution occurring. In spite of this, because the universe is so enormous in space and time, especially at the end of all the stars, in some models of heat death, they would eventually outnumber any observers that arose through normal cosmic evolution, especially in other universes that would have different rules or physical constants, which leads to a deeply unsettling implication. If most observers in the universe are random fluctuations, then statistically, any given observer is more likely to be one of them than part of a long, structured history. Essentially, you're a lot more likely to be a delusional Boltzmann brain hallucinating this reality than actually experiencing it, much as a simulation hypothesis. And since you are a crazy madman dreaming in the void, you can't necessarily trust any of your observations about the outside universe and what they might tell you about the probability of your own existence. It is one of those ideas that tells you something about the limits of a theory by making it uncomfortable to accept. A universe that lasts forever may not end in silence. It may end in madness and confusion. Poincaré Recurrence. The universe tries again. There is one final twist to a universe that lasts forever, as was the case in the steady-state model, or in its precursors in a post-Newtonian or pre-Einstein view of physics that Boltzmann and Poincaré both lived in. If the universe is finite in its total possible configurations, then given enough time, things like Boltzmann brains must occur. Any random collection of atoms, no matter how big or seemingly organized, must pop up occasionally and repeatedly. By this same reasoning, any system must reset itself after enough reshuffling. Shuffle a deck of cards long enough and it will go through every possible pattern, including the first one it was in when you got it. Add more cards and it becomes way less likely, but on infinite timelines, just as certain. Make a universe-sized deck of cards, or atoms, and this is still true. This is known as the Poincaré Recurrence theorem. Over timescales so large they defy notation, every possible arrangement of particles can occur again, including ones that look very familiar. A galaxy forming, a star igniting, even an entire universe that looks like the one we started with. Not because of a bounce, not because of new physics, but simply because eventually random chance runs out of new things to do. Given enough time, even the impossible becomes inevitable. Now, in a Big Bang theory of the universe that keeps expanding, this does not happen, because the deck of proverbial cards keeps getting bigger. Your deck never resets if you add options faster than you can shuffle through them, And all that new expanding space is just that, basically. New cards, new places for things to be. However, you may have noticed as we've gone through today that a lot of these ideas assume there might be something bigger than the Big Bang, wider or older or higher realities, often ones that have the same kind of requirements that encourage folks to think of the steady-state universe concept in the first place. The Omega Point, a final burst of thought. There is one more idea that takes information perspective in a very different direction. Proposed by Frank J. Tipler, the Omega Point is tied to a collapsing universe, the Big Crunch or bounce models we mentioned earlier. In this scenario, as the universe contracts toward a final singularity, energy densities rise without bound. If advanced life or intelligence exists at that stage, it could, in principle, harness that energy. As the collapse accelerates, computation speeds up, faster and faster, approaching an infinite number of operations in a finite amount of time. From the outside, the universe ends in a final instant, but from the perspective of whatever is doing the computing, that instant stretches into an eternity, an infinite amount of subjective time experienced before the end. It is a striking idea, and when we explored more in our Omega Point cosmology episode, a universe that doesn't end in darkness but an explosion of thoughts. But it comes with a major caveat. It depends on a universe that eventually collapses, something current observations do not support. So while it's one of the more imaginative endings, it's also one of the least likely. The Information Graveyard, a universe of isolation. Even without reaching those extremes, there is a quieter informational ending. As the universe expands, regions become causally disconnected. The observable horizon shrinks in practical terms, not because it's getting smaller, but because everything beyond it is moving away faster than light can ever bridge the gap. Over time, galaxies vanish from view, then even nearby structures drift beyond reach. Eventually, each particle or small cluster of particles is effectively isolated from everything else. No signals can cross the growing distance. No interactions can tie distant regions together. Cause and effect still exists locally, but the universe as a whole stops being connected. In some ways, this echoes the earliest moments of the universe during cosmic inflation, when space expanded so rapidly that regions were briefly cut off from one another, unable to exchange light or information. It reminds me a bit of our reset condition from Conformal Cycle cosmology, where the dying universe comes to so resemble the beginning universe as to cause a reset. But there is a crucial difference. Inflation ended. Connections were restored. This time, they are not. What you end up with is not just an empty universe, but a fragmented one. Each region evolving on its own, with no shared history, no communication, no larger structure tying together. In a sense, the universe doesn't just lose its contents, it loses its coherence. Even information becomes local, trapped within tiny pockets that can never again influence anything beyond them. If you imagine a civilization at that stage, it's not just a matter of dwindling resources, it's that the rest of the universe has effectively ceased to exist for you. Not destroyed, not gone, just forever out of reach. In the end, the universe isn't empty, it's just completely alone. So, which ending wins? At this point, we've covered a wide range of possibilities. Some are slow and quiet, some are violent and abrupt, some rewrite the rules entirely. So which one actually happens? The honest answer is that we don't know for certain, but we do have a very strong favorite, and it comes down to what we observe right now. The universe is expanding, that expansion is accelerating, and the simplest explanation we have is that dark energy behaves like a constant. Not growing stronger, not weakening, just steady. Now, there is some more recent evidence that suggests this might not be the case, but if it remains true, then most of the alternatives fall away. A big crunch would require expansion to reverse, which doesn't match what we see. A big rip or little rip would require dark energy to increase over time, and so far, observations don't show that. Most of the more exotic Indians depend on new physics we haven't confirmed. Vacuum decay could happen, but we have no evidence that our vacuum is unstable. Dimensional shifts, brain collisions, and spacetime dissolution all require frameworks that remain speculative, so when you strip all that away, what's left is the simplest path forward. The universe keeps expanding. Structures continue to thin out, entropy increases, and eventually you arrive at heat death. Not because it's the most interesting ending, it's hard to think of anything more boring, but because it's one that requires the fewest things to go differently than they already are. Most Indians require something to change. Heat death is what happens if nothing does. So it wins. For now. He needs to hold that title for many trillions of years, though. This month we're talking about ocean worlds, and one of the ideas lurking underneath that is that planets are not finished objects. Land rises and sinks, seas advance and retreat, volcanoes build new ground, and over enough time, even the most permanent-looking continents are really just temporary arrangements of rock with delusions of grandeur. That's what makes Joe Scott's oldest and newest place on Earth such a good fit on Nebula. Joe takes us from some of the oldest exposed rock on Earth to Hawaii, where volcanoes are still creating brand new land, and it is a wonderful reminder that Earth is not just a place with history, it is a place still actively making history. It is sort of deep-time science storytelling SFA viewers tend to enjoy, and Nebula is a good home for creators following those big ideas properly. You also find my full SFA catalog there, including monthly exclusives like this month's Colonizing Ocean Worlds, Subaquatic Settlements, as well as exclusive collections, bonus episodes, and regular episodes early and ad-free. You can use my link or the QR code to get 50% off an annual plan, or 40% off lifetime access, and it directly supports SFIA and the other creators making these shows. What the end of time actually means. What we mean by the end of time isn't really a final moment. There's no universal last second where everything suddenly stops. Instead, in most of these scenarios, time fades out in a much quieter way. Time, as we experience it, depends on change. Clocks tick because the systems evolve. Events happen because one moment differs from the next. When a universe has reached maximum entropy, those differences disappear. No gradients, no flows of energy, no processes unfolding. Everything becomes uniform. And in that state, time doesn't exactly stop. It just stops meaning anything. There's no practical distinction between one moment and the next, because nothing's happening to mark the passage between them. So the end of time isn't a bang or a cutoff. It's the point where the universe becomes so still, the concept of before and after no longer has any meaning. And even that depends on perspective. To us, a trillion years feels unimaginable, but a system that operates on those timescales might still experience a changing, active universe. What looks like the end of time to us might just be a very slow time to something else. The universe may end in fire, or ice, or something far stranger than either. It might tear itself apart, it might collapse inward, it might quietly fade into uniformity, or simply shift into something unrecognizable. But whichever path it takes, it won't be anytime soon. Even the fastest endings lie far beyond the lifespan of stars, galaxies, anything we would normally call a civilization. And the slowest stretch across spans of time so vast, everything we've ever known fits into the opening moments. We live in a young universe, one still full of structure, energy, and possibility. And while its ending may already be written into the laws of physics, we are still very much at the beginning of the story.